none of your constraints are fighting with each other. They're not trying to do the same job, okay? It's like if you have a project and you put 2 grad students on the same project, that can turn out bad sometimes because they both try and go different directions, they fight, and they don't have ownership over it, and they butt heads, and it's generally not good. It's usually good that if you have 2 grad students, you put them on 2 independent projects and let them do what they want to do with their own project. Well, that's how exact constraint is. If system is exactly constrained and each constraint is doing the unique job of killing its own degree of freedom, it's its own job, then they don't fight with each other. There's no stress buildup. There's no transfer of stresses. There's no bifurcation. All these things I'm going to talk about in a little bit. They don't, they accommodate thermal expansions, and things do what they're supposed to do with high precision. Okay, so you want to make things, anyway, for now you probably don't understand why, but just know that if you want things to be precise for precision engineering, you probably want to exactly constrain it as much as possible. Okay? Okay, but what's the opposite? What's over-constraint? Well, now it's all going to become clear to you, because you can't really understand. If I was trying to teach you what white is, you couldn't understand what white is unless I showed you what black was, or dark and light, or bitter or sweet, or you need the opposite to understand the whole concept. Okay, so here we go. What's over-constraint? Well, let's look at this example here. Okay, say we have this example, our famous example. This is grounded. This guy moves with 4 degrees of freedom. Now say we add this constraint. Okay, right there in the middle, right along there. Which one does that constraint kill? So now it's 6 minus 3, you expect 3 degrees of freedom. Which one does it kill? Okay, put me on pause and stare at it, and then I'll tell you the answer. Okay. Well, say you did that and you thought, my goodness, this doesn't kill anything. Like, it could still rotate here in torsion. It could still translate in all these directions. It could still rotate there. And what's the deal? And then say you were really diligent and catted it and did a modal analysis, you'd find the first 4 mode shapes are associated with natural frequencies that are substantially lower than any other natural frequency. And so that's a good indicator that these 4 are still degrees of freedom. This constraint didn't kill a degree of freedom. Okay, so it begs the question, like, what the heck? We have 3 constraints. 6 minus 3 should be 3, but we still have 4 degrees of freedom. It's undeniable. There's 4 degrees of freedom there. So the question is James Clerk Maxwell's equation wrong? Well, one of the most important principles you learn in this class is James Clerk Maxwell is never wrong. He's like, the guy's a total genius. Everything he says is right. So something's wrong about us here. So we need to reconcile what in the world is going on here. Okay, so remember though, so first of all, what's going on here is that this was a redundant constraint. Okay, so what is a redundant constraint? Well, a constraint is redundant if it has no effect on the flexure system's kinematics. If it does the same job, if it's like you have a higher grad student do the exact same job, and they literally do the exact same job. Say it was possible to get like an absolute clone of a grad student, and they did the exact same job. Well, it's like that the grad students are doing the same thing. One is redundant, right? So this constraint is not doing anything different than these constraints. Okay, it's still killing the same 2 degrees of freedom. All 3 of them are working together to kill just those same 2 degrees of freedom. The translation here and the rotation here. It's not. You could add it or take it away, and it wouldn't change anything about the degrees of freedom. That's what a redundant constraint is. And you always ask yourself, if I add it or take it away, would it change any of the degrees of freedom? And if the answer is no, then that means it's redundant. Okay? And so here's where James Clerk Maxwell was tricky on us, is he said C is the number of non-redundant constraint lines. But I couldn't tell you what that was because you didn't know what that was in the past. Okay? So this equation is true as long as C is a non-redundant or independent constraint line. Okay? So in other words, this equation is true if it's exactly constrained. So if for every constraint you add, it takes away a degree of freedom, then the system is by definition exactly constrained. And when R becomes 0, it's totally exactly constrained, right? But if the constraint doesn't kill a degree of freedom, then it's redundant, and it's said to be over-constrained. Okay? Now, the question is, which constraint is redundant here? Okay, well, you'd say to yourself, well, it's obviously 2 because when I added it, it didn't do anything. So this is the redundant one. Well, don't be so quick to judge. If I take out 1, this is basically the same system. How close they are doesn't matter if they're ideal constraints. They're still infinitely stiff along their axis and infinitely compliant in the other direction, so how close they get is irrelevant. And if I take this away, it wouldn't add or subtract a degree of freedom. Same thing if I take 3 away. So it's any one of these 3 could be the culprit. Okay, so there's no one that can be blamed among those 3. One of the 3, whichever one it is redundant. Okay, so that's another principle to think about. Okay, but again, anytime I have a redundant constraint, one or more redundant constraint, it's over-constrained. Okay, now remember, it's still a true principle. If I add a constraint, I'm never going to kill more than 1 degree of freedom. But now I've shown you a scenario where sometimes when you add a constraint, it doesn't even kill 1. Okay? So that's always true. If you add a constraint and it kills 1, it's exactly the same. If you add a constraint and it doesn't kill 1, it's over-constrained. And by the way, once it's over-constrained by a single constraint or more, the whole thing's over-constrained. Okay? So you know, I could just keep adding. I could add a 4th one that's parallel to. I could add another one right here. I could just keep adding them, and it's gonna over-constrain it more and more and more. But once there's even one bad child in there, one bad thing that's redundant, the whole thing's considered over-constraint. To be exactly constrained, this equation has to work, and they all have to be doing a unique job of killing a degree of freedom. Okay. Okay, so let's talk about the good and bads of over-constraint here, okay? Because over-constraint's not always bad. I've probably painted it like it's like the bad guy, okay? And oftentimes it is, but it doesn't have necessarily bad things. So let's look at this system here. This is a flexure system, and if I ask you, is this a parallel or serial system? Many of you might say it's a serial system because you see multiple rigid bodies, okay? It's not just 2. Well, you're wrong, because what you need to do is look carefully and see the hatching tells you what's grounded, and you might as well think of this as one big rigid stage here that's just grounded. So we actually do have 2 rigid bodies connected directly to ground by flexures. Okay? And yes, these wire flexures are in parallel. They may look like they're serially stacked, but they're not, because this is one common ground, and these are directly connecting it. And one way you can figure that out, remember, parallel systems, serial systems always experience the same force through them, but different displacements, right? But parallel systems always experience the same displacement, but different forces. So, for instance, if I say this is thicker and this is thinner, if I displace this, they both are forced to move the same amount. But the force in the thicker one is going to be bigger than the force in the smaller one. So that tells you it's parallel, because they both were subject to the same displacement, but different forces. I mean, in this case, they're the same forces because they're the same stiffness here. But anyway, trust me, it's parallel. Okay? Okay, and it's redundant, right? Because if I just got rid of this whole side, this single wire is already doing the job of killing this translation. It can allow a translation there and rotation there, but it's killing this translation. By adding this through the same axis, it's not doing anything different from a kinematic standpoint. It still is just killing this. They're both fighting each other to kill that, but they still both are allowing the rotation. So you've got 2 constraints, and they're only killing 1 degree of freedom. So they're fighting with each other. Okay. The rigid analog is this, where you just you have direct contact between these 2 pins, and they're only touching along a blue line. These pins are both doing the same job of constraining it, so it can't translate. But in this case, they could both rotate. They could both translate, and it could rotate there if this were just for just little amounts, right? If you got rid of this, you can really see it can rotate around this axis, right? So, okay, so all right, but yeah, even with both, you could rotate around really any axis through here, right? You could hopefully visualize that. It wouldn't be constraining it. Okay, so with that understanding, knowing that those are indeed both over-constrained systems that have a redundant constraint for both the compliant and rigid analog, let's talk about the pluses and negatives of over-constraint. So first, let's do the negatives. Okay, so let's look at the right here, the negatives. The reason I show the rigid analog here of over-constraint of 2 things that are just imparting a single kind of blue a constraint line, is that it's very clear to see that you're either going to have a scenario where it's loose or binding. Okay, so it's clear to see these guys are fighting each other, why it's bad. Okay, because the fact is, if it was a perfect world and those pegs had the perfect amount of atoms in them, oriented the exact same perfect thing, you could put it in the perfect hole and this was all perfect, then okay, maybe if there were perfect clones of each other, they could do just as good a job of one. But the fact is, there's no two things that are identical. Like I said, there's no grad students that are identical. They'll think of different things on the same project, and they'll kind of butt heads and everything. I suppose that could be good for some scenarios. But you know, as far as the grad students go. But in design, if you have constraints that are doing the same thing, it's either going to bind or it's going to be loose. You're never going to find it to be perfect. Okay? So because they fight with each other, there's stress buildup. And what can happen is things can bifurcate, which means you know, there's weird non-linearities, and over the deformation path, depending on how you load it, it can start taking a different force displacement plot and split and just do weird bad things that you don't want because the constraint's doing the same thing. They're fighting against each other. Okay? Now you could say, well, this one, that only happens if you assemble them. And yes, if you take things that are imperfect and everything's imperfect and you assemble it, you're going to assemble it imperfect. And the fighting of redundant constraints is going to be even worse, right? This is why it's clear these are two different pegs in a board. You assembled this. It's clear for you to visualize. That's going to be a problem. But this guy, say you cut out with a wire EDM, you could say, well, I didn't have to assemble it. It's actually it was one sheet, and I cut it, and so maybe it is perfect. Well, wrong. Every material has residual stress built in it. When you cut it out, that residual stress will be released, and maybe this guy will expand or something more than that guy when the residual stress is released inside the sheet, and they will be fighting and binding and jamming. Or maybe it is perfect and you're able to get no residual stress in your sheet that you cut it out of, but now say you put more heat over here, and this one gets hotter and that one's colder, and so this one expands more than that one, and now those guys are fighting each other and binding and jamming and doing all sorts of bad things, right? So there really is, you know, you're going to have these problems no matter what if you're over-constrained, okay? And the less redundant constraints you have, the less issues you're going to have with over-constraint, obviously. And the less you assemble stuff, the less issues you're going to have. So know that all the negatives with over-constraint get worse if you assemble the system and you have even more redundant constraints. Okay, so the less over-constrained you get and the less you assemble, the more you can just cut it out of a single piece. It will make the problems of over-constraint go away. Okay, but it'll never fully go away unless it's exactly constrained. Okay, I almost said totally exactly constrained, but remember, totally exactly constrained means there's no degrees of freedom. Okay, so that would have been wrong. Okay, so the other downside to it is it takes extra material. It's an extra peg. It's like, who needs an extra peg, especially if it's hurting? Okay, well, and for the rigid thing, you might say, well, but if you get rid of this, then this guy can translate away. But if you took my 162A class, you know you can never break a joint, even if it's obvious you could easily separate it. You know, you're not allowed to mathematically. So you assume this is always kind of preloaded against this. A single peg will do a lot better of doing the job of constraining it along this blue dotted line here. I mean, it's not blue, but it could be drawn blue for the ideal constraint thing. It does a lot better job, and you're not allowed to separate it. It's just like wires. You're not allowed to buckle them. You assume they're infinitely stiff along their axis in compression and tension, okay? And infinitely compliant in the other direction. So from an exact constraint standpoint, you definitely want to just use one peg and make sure it's preloaded against it, and it'll do a much better job. And for this one, if you cut this off, this will do a much better job of just killing the translation with no fighting or no stress buildup and all the issues, okay? And like I said, you get to save a pen and you get to save a lot of this material because you're not using it, okay? So it's lighter weight, etc. Okay. So those are some of the negatives of over-constraint, okay? But there can be good things to over-constraining something, okay? So it's not always bad. If you can tolerate, oh, and by the way, you'll always lose precision the more you over-constrain things. It won't be as repeatable because of this binding, jamming, stress buildup, bifurcation, nonlinear, all these things. it's not going to behave, repeatably the way you want. Okay. Okay. So if you really care about precision and you're moving atoms around and stuff and picometer resolutions and all these things, you definitely want it to be as exactly constrained as possible. But sometimes you don't need that much precision, and there's some good that comes of over-constraint. Okay. So for instance, if you over-constrain this, in this way, you can increase the load capacity, the stiffness, and the dynamics without changing the degrees of freedom. So for instance, if I get rid of this guy and I push on it in this direction, in reality, this could buckle. Okay? But if I add this guy and I have this in its ground and I push on it this way, this guy might try and kind of buckle, but there's no way this guy's going to let it. So it'll have a much higher load capacity. It'll be able to withstand a much higher load. And that can be really good if you're stronger, right? And say you want to stiffen it, but you don't want to, say this is gone, say you want to stiffen this, but you don't want to get this thicker and thicker, because the thicker and thicker it gets, the less of an ideal wire constraint it behaves like. It starts constraining other directions, right? So how can you stiffen it but without changing the geometry of this? We'll just add another guy that's doing the same thing. Now, it won't change the degrees of freedom, but it will make it twice as stiff, right? Or in this case, you can make it even more than that, because instead of just, if you move this up, instead of just bending, these guys will actually stretch. So you can dramatically improve the load capacity. You can dramatically increase the stiffness without increasing much mass, which, by the way, increases the natural frequency, square root k over m, the natural frequencies, right? You can increase the stiffness without increasing the mass much by over-constraining things. And so you can get a larger bandwidth, which increases the, improves the dynamic characteristics. Okay, so by over-constraining, making something symmetric, you can increase load capacity, stiffness, and dynamics, all without changing degrees of freedom. That might be really great. The other thing is symmetry is a really important principle in design, right? Like, if you look at me or anyone else, we're symmetric right down the middle. And the reason is because redundancy is actually really good. I mean, if you have two eyes and one goes blind, you can still see and survive in the other. If one kidney goes, you still have the other kidney. Like our whole body is symmetric so that we can have redundancy. In case one system fails, we have the other one, right? And symmetry fixes all kinds of issues in design. So for instance, say you didn't have this and this guy's there. Well, sure, the degree of freedom is a translation and a rotation. But if you actually translate it at some finite amount, now you're actually talking about motions, not degrees of freedom. This guy's going to arc like this if this guy's not there. Well, if you make it symmetric and you push up, the degree of freedom now corresponds with the motion, because this guy's not going to be able to arc. This will be pulling it in both directions, so it'll just go straight up and down. So you can fix what's called parasitic error. Parasitic error are unwanted stray motions that are accrued after you're going the motion you want, that are unintended. So if you got rid of this, you intend it to go straight up, but because of this flexure over large deformation, it starts pulling it a little bit in this direction, arcing. That's a parasitic error. So you can get rid of parasitic errors by making things symmetric. And make the degrees of freedom actually correspond with a large deformation motion. So same thing with this. As you rotate this, without this, it might start tucking in. But here, if you keep rotating this, the axis of rotation stays put. The other thing is symmetry helps make things thermally stable. Remember, if you didn't have this guy and it was just exactly constrained, you heat it up, this guy would drift over that way, right? But by making it symmetric, if you heat it up, this guy is not going to move much. Of course, these guys will try and jam each other. It might rotate a little bit to accommodate, but the motion is much more thermally stable than it would be otherwise. Okay, so over-constraint can be necessary to make things symmetric and to get rid of parasitic errors, to fix thermal stability, to increase load capacity, stiffness, dynamic characteristics. All these things make it better. But again, you're going to sacrifice some precision. So it's like pick your poison, So, but it can be good or bad. Okay, under-constraint. All right, so let's look at under-constraint here. Okay, so again, you are either exactly constrained or over-constrained. The second you have a redundant constraint, you're over-constrained. You're no longer exactly constrained, right? If you're exactly constrained, you're not over-constrained. These are two of the same concept, but they're opposites. You were either this or you were that. You were either this or you were that. Okay, those are the opposites. This one is a totally different concept. Okay, you can be over-constrained and under-constrained. You can be exactly constrained and under-constrained. Okay, what you cannot be is under-constrained and not under-constrained. That's the opposite. You are either under-constrained or you are not under-constrained. Okay, so what is under-constraint? Well, whereas over-constraint occurs when you have redundant constraints, under-constraint occurs when you have redundant degrees of freedom. Okay, so that's key. I'll say that again. When you are over-constrained when you have redundant constraints, but you are under-constrained when you have redundant degrees of freedom. Okay, well, how do you have a redundant degree of freedom? Well, you can't do it with a parallel system. So just look at this guy. This is a parallel system. It's two rigid bodies connected directly to ground by this, and it achieves this nice translation. Okay, when you have a parallel system where one ground, one stage, and these guys are stuck to it, okay, then right, you have some set of degrees of freedom it achieves. In this case, it's just a single translation. Well, none of those can be redundant because it's a single body. It has whatever degrees of freedom it has. But once you stack it in series, this is now truly a serial mechanism because here's one parallel module, and then it's like here's the other parallel module, and its ground is basically stuck on the last one stage, and now this intermediate body, and that's now the stage. So it's got two parallel modules in series, single ground, an intermediate, and a stage. So there's three rigid bodies, and one's ground, one's intermediate, one's a stage. So that's truly a serial system. Okay, so now we have the ability to have a redundant degree of freedom. So remember, this guy got a translation, but now that guy's got a translation. If I hold this fixed, this guy can translate. Okay, but if I held this fixed, this guy can translate, right? So and they're the same degree of freedom. Remember, even though I show them in different, this one is drawn there, this one's drawn there, even though they're, they appear to be drawn at different locations, they're translations. And translations don't have locations. They're both pointing in the same direction, so the same degree of freedom. They're redundant degrees of freedom. And so this system is said to be under-constrained because it has redundant degree of freedom. This body had the same degree of freedom as that body. Okay? And as a consequence of these redundant degrees of freedom, the system is under-constrained, meaning now say I fix this final stage fixed with respect to the ground, you ask yourself, can this guy move? Yeah, it can still translate with the redundant degree of freedom. So usually with flexure systems, all you care about is the stage, the final system. Usually you have your actuators, your sensors on that, and you're moving around. And you only have independent or intermediate bodies with flexures connecting things in series just to constrain things to move the way you want, right? And so you can typically only control the stage with your actuators, and you're measuring the stage and stuff. But if you have a redundant degree of freedom in a serial system, if they have the same degree of freedom and it's under-constrained, meaning you lock this, and this guy can still bob, then this guy's unaccounted for. It can vibrate, and it can do all kinds of bad things that you can't control with your actuators, okay? Okay, so hopefully you caught that parallel systems cannot be under constraint. So if I ever show you a system on an exam, which I will, and I'll say, is this under constraint, or is this parallel or serial or hybrid? If your answer is parallel and you're correct, and then if I later ask, is the system under constrained, which I will certainly do on an exam, and you say, well, then your answer should be no. And the reason is because it's parallel. Parallel systems cannot be under constrained because they can't have redundant degrees of freedom. If you hold the stage fixed with respect to ground, obviously nothing can move. There's no body to even be able to vibrate or move. Okay, so parallel systems don't even have an intermediate stage to be under constrained, and they only have one stage to have degrees of freedom. You need at least two stages, two bodies, this one and this one, to have degrees of freedom to even be redundant. Okay? Okay, so only serial and hybrid systems can be under constrained. And they're not always under constraint. Sometimes they're not under constraint, but the way you can tell a serial or hybrid system is under constrained is there's two conditions. If they have redundant or the same degree of freedom, And if you can hold this fixed with respect to that, and this guy can still move. Okay? And they're both the same condition, but it's two different ways to think about checking it. Okay? So let's do a different example. Let's look at this guy. This guy has two rigid bodies, this one and this one. I wish I had drawn this thicker, and I wish I had drawn the blade thinner. But anyway, here's a rigid body, here's a blade flexure, and here's a rigid body. Okay? So this guy achieves multiple degrees of freedom, but here's 1 degree of freedom it does. It does this rotation up its axis. Okay? It can do this torsion thing. Okay? Well, what if I now, so then this is a parallel system. Two rigid bodies connected directly to each other, that's it. Okay? So if I asked you, can this be under constrained, your answer would be no. It's a parallel system. If I hold this fixed with respect to this, obviously nothing can move. Okay? All right, but now say I stack this guy in series with itself. So now we've got two parallel modules stacked in series. We've got three rigid bodies. One is ground. We've got two bodies that can move. Here's this one. Here's the stage that you care about. Okay? And I stacked them. Notice I turned it 90 degrees, whatever. Right? They both independently achieve this same rotation. And that rotation is in the same location, in the same direction. So it's the same degree of freedom. So if I asked you, is this under constrained, you'd first say, well, it's serial, so it can be under constrained. But the question is it? Does it have a redundant degree of freedom? Yes, it does. They both have, this one has this one, the other one has this one, and they're both aligned. So yes, they have the same redundant degree of freedom, so it's under constrained. And again, what's the final check? If I held this fixed with respect to that, could this guy still move? Yes, it could. It could rotate around this axis, okay, in an under-constrained way that actuators and sensors couldn't correct for, and that would be bad, okay? All right, so let's do one other example. This is a serial system, obviously. Here's the ground, here's the intermediate stage, and here's the final stage, okay? So this one's a nested one, but it's still in series, but it's nested inside of itself, so you can get a lot more range in the same size, okay? But you can see it's basically the same mechanism put inside of itself. And it's obviously serial. It's two parallel modules stacked in series, okay? Okay, so if I ask you, is this under constrained? Well, you'd first say, well, it's not parallel, so it could be, okay? And then the second thing you'd say is, do they have the same degree of freedom? Well, sure they do. If you think of this guy grounded, this guy can translate. If you think of that guy grounded, this guy can translate. They both translate in the same direction, and so it's redundant degree of freedom. And you could imagine if I hold this fixed with respect to that, this guy could still move in an uncontrolled way. So this is definitely an under-constrained system. Okay? Now, of course, what's the negative of under-constraint? Again, under-constraint can have positives and negatives. The negative is, well, one, I mean, this is a stupid reason, but there's extra parts of material. Like you're stacking things in series. You have, if this was parallel, you get rid of it and there's less mass. I mean, but that's stupid, right? So the real negative that you care about is there's worse dynamic characteristics, okay? So in a system, if you have a big fat mass that's not constrained, if you hold all your actuators are driving this guy, and your sensors, and they're usually attached to the ground, driving these, controlling these. If you lock it up, say turn off your system, your actuators are locked up, this guy can still vibrate. And when it's working, this guy can vibrate in some uncontrolled way. That's going to shake your system crazy. Even if it's quasi-static, even if you're moving it in very low speed scenarios, the fact that it's not constrained, it's under constrained, there's this intermediate body that can wag around, causes remarkable issues in machines. So if ever you see vibrations or weird chatter or something, certainly if it's a high-speed thing, say this thing's attached to a motor that's going at high speeds or something, you're going to have some serious issues. But even when it's a quasi-static, still-driven thing, you'll have issues, okay? And people don't know why, and you'll be smart and say, well, it's because it's under constraint, so let's fix that, okay? But sometimes you can tolerate the negatives of under constraint, and sometimes you want it to be under constraint because there are some real benefits to under constraint, okay? So again, it's like pick your poison. Whereas over constraint isn't always bad. Sometimes it's really good to be over constrained. Sometimes really good to be under constrained. Here's where you care about being under constrained, okay? So, or here's where it would be good. Well, first of all, if you've got this guy, anytime you stack something in series with the same degree of freedom, you're going to get twice the range out of it, right? So this guy can move twice the range as this guy. okay, before it yields, right? Because this guy moves its amount up to its yield point,